One of the things that I have always loved and admired about space exploration is that it is driven by this collective desire to understand more about how our universe began, what state it's in today, and why it is that way. Scientists can get a great deal of insight into these questions by measuring signals in the Terahertz spectrum, which includes frequencies on the order of 10 to the 11th and 10 to the 13th hertz. The Terahertz spectrum gives us information on the composition of interstellar gases, the detection of water on other planetary bodies, and other dynamic processes in planetary atmospheres, such as radiation balance, changes in our ozone, and volcanic activity within our solar system. By studying our universe this way, we can peer into the early days of the universe to better understand its state and composition, along with how it has developed over time. And if any of that intrigues you and you're interested in what kind of technology goes into helping us get this information, then stay tuned for this epic two-part series. Hello, and welcome back to another episode of The Art of Space Engineering, the podcast which aims to explore the details behind how spacecraft and various payloads come together before launch and the lessons learned along the way. I'm your host, Sarah Rogers, and in today's episode we'll be exploring some antics in the Terahertz spectrum. As I mentioned before, the science that you can do with these higher frequencies is pretty powerful, but making this possible requires precise instrumentation that can collect data as accurately as possible, so that way we can learn as much as possible with the information that we gather. And there is a heck of a lot that goes into these systems: cryogenics, optics, signal processing, well-designed thermal control, etc. I will stop myself there before I get carried away. Today, we're only going to focus on one aspect of these systems, which is low noise amplifiers. These boost an incoming signal captured by a telescope using very low noise electronics, so the signal is very clear and distinguishable from other unwanted signals that are introduced by the system. Now, these electronics are being actively developed in world-class research facilities and in a basement at ASU. Now that is actually not as lame as it sounds. The basement of ASU's ISTB-4 building has some pretty top-notch facilities, some of which are dedicated to developing these low-noise amplifiers to aid terahertz research. It's also where we developed and assembled the Phoenix CubeSat, which, if you are new to this podcast, was a CubeSat that I worked on at ASU to study urban heat islands. So in today's episode, I got to chat with Justin Mathewson and Jonathan Ho about their work in ASU's Terahertz Lab, the science studies that result from it, and the antics that ensue along the way. This includes the tale of the Great Basement Flood, which was a wild day, and if you want to hear about that story, that's in part 2 of this episode. The projects they work on are so cool. They're the type of thing that gets me really excited about space research and remind me why I chose this field in the first place. So I'm really excited that I got the chance to do an episode on the work that they do. We actually ended up talking for like 3 hours about all of this and like a bunch of other things. And I wanted to keep as much of it as possible because I just loved all of it. It was a really fun conversation to have. So I split this episode up into 2 parts, so if you enjoyed this conversation, then definitely go and check out part 2. Also, one thing I do want to note about this episode is that it was recorded like way back in September before school and work just got really busy. So that, hopefully helps you understand more of the context of what we're talking about in the beginning of the episode and where things in the lab were. But that is enough of my rambling introduction, and so now, without further ado, let me introduce the Basement Dwellers.
Hey.
Welcome.
How's everyone doing?
We're good. Sarah just went to go turn off her AC.
Yes.
So how does this start off? Do we do some witty banter and then go into intro?
Yeah. I might want to move downstairs quickly so I'm closer to my router.
Okay.
Because every once in a while will run into an issue where I cut out.
Sounding like a robot.
Yeah.
Okay.
I do sound like a robot a lot, yeah. So I don't want that to happen. Do I sound like a robot right now?
No, you sound normal for once.
Good. Yeah, now my internet has been fixed in recent times, but I'm still nervous about it. All right, I am set up.
All right. So I guess with that, let's get started, and then we'll just kind of go with the flow and see where that flow goes. But yeah. But But yeah, thank you guys for joining me and taking some time out of your Saturday to talk about what happens in the mysterious basement of ASU's School of Earth and Space Exploration. So I figured let's just start off with some introductions and get to know you guys. So why don't you just talk about your background, what you're doing at ASU, and any other interesting tidbits that you want to share.
Yeah, you can go first, Justin.
Hello, for all those cats and kittens out there. I'm Justin Mathewson. I'm a research specialist in the Terahertz lab at ASU. I work for Chris Groppe and Phil Malstoff, and I essentially test and build low noise amplifiers pretty much all day.
Yeah, Justin's got the best hands in the business.
People say that. I'm not sure there are studies.
That's the catchphrase we all say, you know.
It
You're
is.
really the only like LNA engineer I know, so I might be a bit biased.
Yeah, I get the compliments like, wow, your hands are so steady. It's like, are you kidding me? When I look at the microscope, it's like wiggling every which way.
Well, but
yeah, it's because
those LNAs are small. Like I would imagine you'd have to have absolutely steady hands to do that.
You know, you wouldn't need them to be as steady as you might think.
Well, Justin, you also drink considerably less caffeine than about anyone else in the entire laboratory, which is maybe why we all think you have such steady hands. Everyone else is on a diet of like 6 to 7 cups of coffee a day.
I do not drink coffee. I drink it very rarely, like maybe 3 times a year.
Yeah.
Wow, how bad does it have to be to get you to drink coffee then?
Ooh.
Like all-nighter
No, actually, I can deal with an all-nighter. It's really a matter of if I've gone to sleep and it's only been like 2 hours, and then I wake up and it's like, I can't like function. That's when I need to drink coffee, because I've had times where I feel like I don't know where I am. I'm actually falling over like I'm a drunk person, and it's just, what is happening?
Yeah, there was also that one time Justin and I judged a hackathon, the Sun Hacks hackathon for ASU. We were the judges for the hardware portion of it. And I brought like 2 Bang energy drinks that day because they sell them at QT for 2 for $4. I mean, like, you can't give up that deal. And I gave Justin one of them in the morning because he just wanted a little. He drank like a quarter of the Bang energy drink, and his body was just like vibrating. It was pretty funny to watch.
Yeah.
I was like, man, I drink like 2 of those a day.
Yeah, caffeine doesn't affect me well.
Yeah.
Give me some of your natural energy because I like don't have it anymore.
Yeah.
I wish I could. I think it's starting to get to the point where I'm going to start drinking coffee, but I think that's because things have started ramping up on the projects.
Before we segue into the projects, John, you should
right. Yeah, I have to
introduce
myself. Yeah. My name is Jonathan Ho. I am I am in my 5th year of my doctorate. Yeah, my 5th year of my doctorate in astrophysics. I am also doing a concurrent master's in electrical engineering. I got my BS in astrophysics from University of Pennsylvania. I graduated there back in 2016. And I did, when I started at Penn, I wanted to do more like the theoretical side of things. I specifically, like in undergrad, like astrophysics, unlike ASU, was just the physics program. And then you specialized in your last couple semesters. So it was like you do a normal physics track, and then at the end you could take extra courses in quantum or E&M, and mine were in like cosmology and stuff. And I did the whole track because I really wanted to take GR from a professor there.
What is GR?
Professor Corey. General relativity, sorry.
Oh, you're good.
I really wanted to take it. Yeah, so that was always when I was in high school, I like realized I liked physics. I was supposed to go to Wharton. I was like slated to be a business student at Wharton, and then at the last minute I decided I wanted to do physics because I really thought space was cool. And my whole goal of going to college was I wanted to take general relativity because, it's like this beautiful culmination of all of modern physics, Einstein's grand theory and stuff like that. And it was really cool when I finally took it. But by that time, I realized that theory sucks. Pen and paper work all day and like doing computer simulations all day is not like the lifestyle I really wanted to live. So when I got out of undergrad, I had experience working on BLAST, which we might talk about a bit today, which was a balloon mission, because I worked with James Aguirre at Penn, who works with Chris Groppe and Phil Mauskoff at ASU. And I got some experience working on like cryostats, which are, you know, for people who don't know, are the giant like super refrigerators that we put on telescopes. So you like take this giant refrigerator and you cool down your superconducting detectors in there to almost absolute zero, like 300 millikelvin, so 0.3 degrees above absolute zero. And you put them on a balloon, and since they're so cold, you can do crazy superconducting electronics with them and get crazy detection levels and sensitivities and stuff. And I got experience with the engineering of that stuff, and I realized that, you know, that was more of the route I wanted to take, was the working with my hands, actually building and designing these things. So when I came to grad school, I met Chris and stuff, Chris Groppe, and I thought his projects were super neat. He was building all these crazy satellites and instruments and stuff like that. And I realized that I was completely lacking in knowledge of electrical engineering and E&M. I think that most people, vast majority of people who aren't electrical engineers, avoid electrical engineering in undergrad because it looks awful. You know, you see these kids in electrical engineering 102 doing these ball of resistor problems, you know, where they're sitting there solving these like arbitrary circuits, and you're just like, this looks awful. Like, why would anyone want to do this? But when I got to grad school, and I feel like Justin it kind of understands the same thing. You start to work more in the electrical engineering community and see it, and you realize that like the modern world is just controlled by electrical engineering. Electrical engineering isn't solving for voltages at nodes and circuits. It's designing the world as we know it, these digital architectures and cloud structures and information dispersion, you know, just everything that we use today, our cell phones, our computers. And it's awesome, but it is very different than what a lot of people will probably do first in college. So when I got here, I realized that I had to learn all of this stuff. And I started taking some electrical engineering courses, specifically in microwave engineering. And I realized after my third one, I was 5 classes away from a master's. And I was like, screw it, I might as well go all the way. So I've been taking the rest of the classes for that. I just finished over the summer. So now I have all of my master coursework done, and I have a couple years left where I will do finish up my PhD in astrophysics with all these projects that I've done.
Very cool. Okay, to continue that question, Justin, what drew you more to the space industry and to ASU specifically?
Oh, that's a long question. So, not a long question, a long answer. So what drew me to space, I was actually, I think, around 8 years old. And you know those like little toys that always like speak at you or something, or like they give you like, that give you like information. I had a platform thing that just talked about our solar system and gave like relatively great detail of everything. And so that, just hearing like about the planets really got me interested in like what's out there, what can we see, what can we do to travel through it. So then that just kind of grew as I grew up, where my parents would just send me to coding and robotics camps just because I wanted to do it for fun. And they would have us do like the simple build a robot, follow the line using a light sensor or something. And just doing that, I was like, I'm really going to enjoy this. So I kind of figured at a young age, I really wanted to work with my hands on like electronics, and I wanted to do something with space, whether it be like aerodynamics or microwave electronics. I didn't really know what specifically at the time. I just knew that that's what I wanted to do. So what brought me to ASU, well, I got my undergrad there, and I got into CC, which I didn't know was a thing till I got to ASU. Because if I had known, I would have applied for that for my major in the first place, rather than being exploratory and searching. And just like learning about the industry as the degree went on through the years, it's like, wow, I really think I found what I've wanted to do. And I didn't think it would ever be like an actual major. I thought I'd have to go through the engineering college or some way. And that's just kind of how it happened. There was a point in time where I thought I was going to be a college basketball player or just play or be a coach for some high school at some point in time. It would have been more of a side job because I think I would have preferred to do the electronics because it would have been more fun.
Yeah, for people who can't see, Justin is quite tall.
Oh yeah, I am 6'2".
That's it? Oh, I thought you were taller than that.
No.
Oh, wow.
John, we're about the same size.
Yeah, I don't know. I slouch a lot.
I mean, I slouch too, but when I stand up straight and put my shoulders in the right place, it's like, oh yeah, you're 6'2".
That is a whole foot taller than I am, so.
Yeah.
So what do you guys intend to do after ASU then?
Yeah, that's a tough question. I mean,
we don't have to ask it.
No, I mean, it's a good question.
It's a good question, no.
Yeah, I think that, I'll step in first, but I think that we're lucky right now, at least in studying space. When I always wanted to be an astronaut since I was a kid, and I think back when I was a kid, that was like kind of, if you were interested in space, that was the premier thing you could be. Was be an astronaut, because that's about as far as you're going to get in space. But throughout my lifetime, the ability to really research and do things that weren't just academic research, but actual, applicable industry in space have been exploding, especially in the last 10 years, with the, creation of SpaceX and Blue Origin and all of these commercial space industries out there, all of these satellite constellations like Swarm and Planet. The actual industry itself for space is growing underneath our feet, almost completely unattached to us. So there are a lot more options in space industry than I thought there would be when I first started studying astrophysics, because I was interested in the philosophy of life and stuff like that. Personally, I'm not sure if I want to go straight in the space industry yet. I would love to start my own company. I have some cool ideas for things that I want to believe will happen in the future. Some pipe dream visions that I have that I would love to get involved in. But for now, I think that when I get out of grad school, I want to find a job that is interesting to me. And I know that doesn't sound like much, but I feel like during COVID, everyone is having a small existential crisis. I think that I'm realizing that I've loved grad school here at ASU, but a large portion of what I've loved so much is going into the lab every day in the basement, working with 20 brilliant scientists every day and kind of just bouncing ideas off of each other for crazy stuff. And the space part of that is awesome, but now that I'm not in that situation anymore and I'm at home working every day, I'm realizing that I've lost a decent amount of the passion I had because I don't have that social interaction anymore. So if I could, I would like to work somewhere where I have interpersonal communication with people and solving big problems. There are a lot of cool labs in Boston. Like there's an offshoot of Lincoln Labs that a few of our graduates have worked at. That would be cool to work at. But just anywhere where I get to work with smart people and solve problems would be perfect.
John, didn't you already start your company?
Yeah, I do. I don't want to plug that just yet, but we can plug that close to the end. I am a CEO of my own corporation. It is an industry disruptor. That's a joke. No one can see my face. That's a joke. It's on the horizon. We'll talk about it later.
It's a competitor to
Alpha Core.
Yeah, Alpha Core. Called it Beta Shell.
Gotcha. Yeah, I didn't know if those stickers were real, like the stickers for the company were real in there, or if it was all.
Yes, they are. Yeah, I do pay a annual fee for my own LLC called Beta Shell LLC.
Just explain the entire, how it began was the funny part.
Yeah, I'll go through the whole story at some point.
Okay.
But I want to hear what Justin wants to do because I'm actually curious about this. I guess what I'm curious about is on a daily basis, you work alongside like the PIs for some NASA missions and stuff like that. And you are essentially a pair of hands who knows what you're doing when it comes to building low noise amplifiers.
I wouldn't necessarily call myself working alongside the PIs. I think I'm more of the underman of the person who works along the PIs.
Okay. Well,
yeah, because Hamdi is the one who like, he goes to the meetings and then him or Chris like tell me, go do this. Like,
right. So they tell you what needs to get built and you and Hamdi figure out how to build it.
Yeah.
So what part of that job, like, would you want to continue doing in the future? You know, like the building part, the problem solving part, the space part, the engineering part, you know?
The engineering, the space part, and the design part, which I want to get better at, which I've been working on since COVID hit, which has actually been a lot of fun. Just trying to figure out how to use CAD like SolidWorks,
Yeah.
CAD, although I wish it was like a little more user-friendly.
It will be.
It's still like nice to learn to use, but it's one of those things that if you're not doing it all the time, you kind of just forget
how
to do it. And then you just got to relearn again.
Yeah.
But yeah, I think I prefer to keep doing the space part because it's space. Space is cool.
Yeah, space is cool.
The engineering part, because I've always wanted to work with my hands, just build and test and just design, because like I want to actually create something without it being someone else's creative property.
You could do that at Beta Show.
Yeah. I mean, I plug this to you all the time. Like, hey man, you ever need someone to come over and create and be like kind of a creative dude, like I'm your guy.
Yeah. Yeah, I know.
Yeah, it's your first employee.
Yeah. Well, we already have employees actually.
Oh.
Yeah.
We got really serious about this for like a week and a half a while ago.
Week and a half. It was like a good month.
Yeah, I guess COVID would probably COVID probably does that for not being able to be in the lab so much. But yeah, to circle back around to what you were saying, John, I would definitely agree with that. I think that was one of the that was a fun part of being in the lab and working on Phoenix, because you're just, everyone's sitting around a table and we're programming a satellite and we're solving all of these problems. And then you have your witty banter with your friends, and it's basically you're working on these really awesome projects for space with your friends. And
right.
It was just the greatest. It was the greatest thing ever. Like I just wanted to do it all day. And I loved that our lab was next to you guys, because we kind of got some of the, some of your guys' work and witty banter and whatnot kind of bled over into our lab. And yeah, it was a fun space. I really miss it down there.
Yeah, I feel like when when you sign up for a PhD program, like you don't really know what to expect, especially in something like astrophysics, where like even though you do an undergrad in it, you don't actually know like what the real world of astrophysics is. You learn how to solve tensor equations, but like what the heck do you actually do in the field? And when I got here, I realized that like, at least for me, and this is not universal for all fields, but at least for the basement crew, like 95% of like what I've learned in grad school so far has come from being in the lab and talking to people. And it's like you have, and this from working on the Phoenix mission, right? Like you have your project that is assigned to you that you work on while you're there. But a good portion of your time is walking around, talking to people, hearing about what they're doing, getting interested in that, and then kind of hopping on their project for a little, bouncing some ideas off of a whiteboard for their project, learning about what they're doing and learning about something else. And that's really like the vast majority of the learning I've done has been from walking around, talking to people, spending a week or two helping someone out while I do my thing on the side. And it does really suck now that COVID has come that like now that 5% that was just me is now the only thing I really have. And it sucks not having all these other sources of information coming to me. I miss just constantly having ADD in the lab, bouncing around between projects, getting into shenanigans, like every Friday. I don't know if I should say this on the podcast, but every Friday we would pull off shenanigans And it would be like fun stuff. We had a giant vacuum chamber in the lab. Sarah, were you there? It was in the Phoenix.
Yeah. Yeah.
Yeah. It's you
Can
know,
fit a
I'm doing
person in
hand
there.
things. Yeah, so I'm doing hand things, but the podcast people can't hear. But it's probably 5 feet across by 5 feet by 5 feet, right? It's a giant metal cube that can get down to like the pressures of 100,000 feet in the air, maybe even higher than that, in like 10 minutes. So we would do things where we would put balloons inside there. We would fill them up and watch them expand to the entire size. We put like peeps in there.
Marshmallows.
We put marshmallow peeps. Yeah, we put all this crazy stuff in there. And we just did so much fun stuff. And you were learning from it, right? Like this was actual learning. And I was realizing things and understanding concepts. And yeah, that's just such an essential part of grad school.
So, does it feel weird to tell people that you work in a basement, or does it actually feel cool?
It's a little both, because it's fun to joke about when you tell people. It's like, yeah, I work in a basement. They hide us from everyone so that we actually get stuff done. And then some people will be like, wait, you work in a basement? That's kind of cool because it sounds like you're the mad scientist in a laboratory, just like building away, just being like Dexter's lab, just get out of my laboratory, Dee Dee, just all that stuff.
Yeah, I agree. I mean, like, I do think that when we say we work in a basement, right, like, there's so much context to that statement, You think of us working in a basement, you think of us in, some damp, cold dungeon. But then you come and you see the building, ISDB4, where we work, and it's this absolutely gorgeous building, massive, built in 2012, completely state-of-the-art. And the basement is just like outfitted wall to wall with just like millions of dollars of electronics equipment in our lab.
Oh, yeah.
So when we say we work in a basement, it's fun because, everyone calls us the basement trolls. And they're, they tell us, they shove us down there. So when we blow things up, it doesn't hurt anyone. But it does feel cool because ISDB4 and CC as a department, right, is it does have a lot of respect from ASU and Michael Crow in particular. This is him and Kip Hodges and a few other people. This was kind of their baby brainchild of a project to combine geology and earth science and astrophysics into this exploratory program. And Michael Crow has a lot of pride in it because, I mean, so far in the less than 10 years that the program's been around, they have done really huge things, the Psyche missions and, countless NASA missions and international missions with other countries. I can't count how many just in the basement we've done with like other nations' versions of NASA. And it does feel cool to be in, a highly regarded department at such a large university and be like the crazy scientists in the basement part of it, Like everyone above us is doing awesome projects. The geologists work on such cool stuff. But it's fun to know that everyone upstairs thinks we're the lunatics in the basement, blowing things up and setting things on fire. And
no one's supposed to know about the fire, John.
Yeah, I know. We haven't lit anything on fire.
Yeah. It was really cool to say that like you worked in a basement because we were telling people about Phoenix. It was like, oh yeah, no, we're building a satellite. It's just we build it in the basement, no big deal. Like it's normal. And then people just always kind of looked at me like, okay.
Yeah, I mean, you had it real. You had one of the best undergrad setups I've ever seen, Sarah. Like, I don't know. I felt like coming from Penn to here, it was like I look back at undergrad and it was like, well, why did I go? Like, I spent so much money on this undergrad education, and like I got to work on some cool projects, obviously, but then I come here and I see you guys working on the Phoenix CubeSat, and it's literally a group of undergrads in charge of a mission to send a CubeSat into space to do thermal readings on the city to watch the heat island or the urban heat effect. And like, it's all run by you guys. Like you have some oversight, but Sarah, you essentially were the PI of this mission, like, and you got to do everything. You guys got to do the hardware, the software. You got to build everything yourselves. You had access to all of this equipment, and you got to learn all of these insane skills essentially on your own and with a significant budget. And I'm jealous that you got to do that. That's
yeah.
a really cool undergrad project you got to do.
Yeah, it's really unfortunate that, you know, it's not like we're going to be able to do exactly this again sometime soon. I mean, we're working towards it, but I definitely think we did get very lucky. And it's definitely a stepping stone to things in the future, because I know they're really working on that with ASU's interplanetary initiative.
Yeah, like it is an extremely unique opportunity, not just at ASU, at any institution. You know, does not matter how prestigious the institution is. Like, it's incredible. I think just like the opportunities that you will have in the future because of that project. And I think that's what makes the most of us the most jealous, right? It's like, it was awesome they got the opportunity, but like leaving undergrad, you actually did a 4+1, right? So
No,
you
I'm
have
doing a
master's.
traditional master's.
Oh, you're doing a traditional master's. So you're in that right now?
Yeah, I didn't. I
Yeah.
don't know. I wanted to do it, but I don't think it. You lose so much from a graduate experience if you just
Yeah.
accelerate the whole process, and so
I
I'm
agree.
really glad that I opted out of that.
But I mean, but regardless, like even if you hadn't done the master's, right? Like let's say you had dipped out right after undergrad, you would have been able to go into the workforce with just an undergrad degree, but also be able to say that you were the head of a small NASA mission, essentially, and you led all these different parts of this project. You did the systems engineering for all.
Uh-oh. It looks like his internet is acting up.
Oh no. Just wait patiently. As long as the whole Zoom meeting doesn't crash,
All these things, and there are so few people.
Hi, John.
Yeah,
Welcome back.
you're good.
Am I back?
Yeah.
Yeah, you're
Yeah,
back.
your
All right.
internet
Sorry,
went out
but
for a
I knew
second.
this was going to happen. Yeah. Anyways, I guess I was just
No,
saying
it's
that.
okay. But I had one where
yeah.
like the whole Zoom meeting just crashed because my Wi-Fi cut out for a minute, and I thought I lost
Oh, wow.
like an hour and a half's worth of content. It was, I wanted to cry. I did not, but it was very scary.
Well, I'll just talk less then, so there's less chance to get cut off.
That is like the worst thing you could possibly have happen, no matter what you're doing. Like whether or not you're testing or building and you're just taking data and then immediately like something crashes on you and you're just like, you lost everything and you just go, you lose your mind. Because I've had that
Yeah.
maybe once or twice. One time was when the lab flooded.
Oh, yeah.
Oh.
The lab flood. That's a great war story
Oh
right
God.
there.
Yeah, we'll save that for later.
Yeah, we'll say that's a good one. That's part 2 of the episode. We'll get into the flood.
Yeah.
Oh my God.
Anyways, yeah, I actually am curious though, Sarah. You asked this question earlier about what we want to do after grad school. I am curious about what you want to do after your master's, because you have a particularly impressive resume behind you, and I'm curious of what you were looking into doing.
Yeah, I've been thinking about that a lot. Definitely going into the industry. But I think in terms of where into space in the first place was because I really liked the exploration and the science side of it. Even though my background's in engineering, so something that is like backed with science is meaningful to me. So places, like places like NASA or Ball, I admire what they do. Is kind of what I've been looking at, and so I've been kind of trying to apply to all of those different places. But I'm not really married to working on like one specific thing that is meaningful to me and is meaningful to an exploration for humanity, because that's the whole reason why I just fell in love with space in the first place. So
Yeah.
there's several things I can do and several places I think I could work where I would be perfectly happy. But one thing that I think this conversation has really made me realize is, or at least remember, is in terms of the experience, what I'm doing, I do love that lab experience of being with people and talking to them and bouncing ideas off and testing things and thinking, oh no, it broke, oh okay, we fixed it. Well, maybe not the last part so much because that's not great, but yeah, that experience, it's just the best. It was the best part of Phoenix, was integration and test and just working with everybody. and you learn a lot from it. You learn a lot in terms of how to make your design better, in terms of communication, and trying to fix things quickly, and also how do I fix things quickly, but not so much to where everyone's stressed out and you end up breaking something again. So it's like this balance of technical challenges and schedule, and I think that's that gets really interesting.
For it's something that you don't realize is that, like, when you work with a good group of people, it's almost like you're in a band, right? Where the sum of all, like, the band itself is greater than the sum of all of the parts, right? Like the lab itself, the whiteboard that you can create going over an idea. If you have, a lab of 6 people, if everyone individually went up to the whiteboard and wrote their ideas out, compare that whiteboard to the whiteboard you would create with all 6 of you sitting there and writing it together. There's no comparison. Like when you are with people who are, synergizing and blending together, the ideas you can come up with are so much greater than, anything anyone could create on their own. And it really is an incredible experience. So anytime you work for the government, right, it's an interesting experience. There's a lot of extra bureaucracy involved, and it's like this balance between, like, when you work in industry, right, it's high pressure, high risk, high reward. And then when you work with government, it's extremely methodical, right, to the point of redundancy and just, almost annoyance. And it's a balance of finding kind of the work environment that fits for you. Do you like more of the methodical stuff? Do you like more of the crazy chaos of the high risk, high reward? But I feel like the issue, and this is something that I'm facing, and I think that we all are facing, is that sometimes you can lose perspective of why you're really in the field in the first place when you get into the job market. It's like, I feel like a lot of us, and personally, I think I got into space originally because I was young, I was 17 or 18, and I was just overwhelmed with the problems in the world and stuff. And everyone kind of reacts in a different way. And, like, to me, it was like studying space and the universe and our existence would give us some perspective. And, like, the understanding that, we as a people are, just a tiny part in this universe would create world peace and all this hippie stuff that I believed at the time that drove my passion. And you forget these things, right? And, like, you love the discovery aspect of it and solving these discovery problems. It's very easy to lose sight of that passion when it becomes your job. Like, they tell you when you're young that if you do what you love, you'll never work a day in your life. And while that's somewhat true, I guess, it's like, that's not a great way of looking at it, because doing your passions will drain you like anything else. And if you turn all of your hobbies into work, you do lose a lot of the enjoyment of it. So, I think it's this kind of quarter life crisis that a lot of people hit when they're academics, where they're realizing that they're losing some of the original passion that they had. And I think that's what drives me and other people I've worked with to think, oh, maybe I'll just skip out for a few years, go make, a couple $1 million on Wall Street, and then I'll go back and help the world, And right, if you go do a PhD, that's like 5 or 6 more years of academia, and it does get long.
That's fair. That's actually, well, that's one of the reasons why I didn't want to do a PhD, but I haven't really found that, like, niche of engineering that would make me want to stay for a PhD.
Yeah. One of these days, if you get a master's, there's you've opened the door that if you ever want to come back and do the PhD, you have the option.
That's fair. Okay. On that note.
Yeah, sorry. I didn't mean to bump you, but I feel like I'm a bad, and no one else.
No, this is fun.
No one else wants
This is
to
fun. This
Wall
is
Street.
good.
That's the conversation. That's what we call the flow, John.
Yeah.
Yeah.
We did say we were gonna go with it. Okay. But to kind of segue off of this. So we've been talking a lot about our background projects you guys are working on in the lab, which are really cool in my opinion. Like, share some of your experience of just some of the projects that you've gotten to work on throughout your time at ASU, and then we'll kind of dive into specific questions with those throughout the interview.
Yeah. Okay. Yeah, Justin. Yeah, you can go. Just what projects have you worked on, Justin?
Or any that you want to share.
Yeah.
You can just share Gustin and Gustin. Okay. Gustin and Simon's Observatory if you want to.
The projects that I've been fully on are Simon's Observatory and Gusto, which, forgive me, I don't know the acronym for it very well, so I have to.
Oh, come on. No one knows the acronyms.
Because I had really had to look up the acronym because I forgot. Gusto, which stands for Galactic Extragalactic, ULDB, which is, oh my God, I forgot.
I think that's ultra long duration.
Yeah, ultra long duration balloon.
Spectroscopic Terahertz Observatory. That is a wordful. Those are the two ones I fully on. Other than that, there was Toltec. Pretty much for that project, I made them stainless steel cables so that they could do readout and whatnot, and amplifiers for that readout chain.
Before you continue, what are all of these projects? What do they do?
Toltec is it's a cryo-cooled telescope that's still in production, still being made, because they were already like halfway through it when I finally joined the team at ASU. So I tried to learn as much as I could, and all I knew was that it was a cryo-cooled telescope on the ground in Mexico, in I think the highest peak in Mexico. It's about traveling up to that mountain. I don't think I want to go there anytime soon, but I have heard about the food, and the food sounds great.
That's right.
Yes.
Yeah.
I know a little more about Simon's, but I'm not at that point yet. But I guess that is a good segue. Simon's is also another ground-based telescope that is in the Atacama Desert in northern Chile. Chile. Now, I don't necessarily know what their objective is. I think John would know that better than I would.
Of Simon's?
Yeah, their science objective. I don't really know it.
For our portion, I know about the instrumentation that we're using for it, but I was only on the project for like a month.
Yeah. I mean, we could just talk about the instrumentation. We don't have to talk about the.
Yeah.
My part was dealing with building and designing an amplifier that had to be 4 to 8 gigahertz and have about 15, 20 dB over about a 12 gigahertz span. And what we came up with was it's a mimic chip based amplifier that uses almost the same components as our normal ones, except it's all wire bonded.
Wire bonding is incredibly difficult for
Yes.
people who have never done it before. It's you have to use like a very specialized piece of equipment with microscopes and do very, very fine precision, essentially wire placing onto pads.
We're talking about wire that's probably about as thin as John's hair, maybe?
Yeah, a piece of hair. Yeah.
Yeah, that thin. But we can go smaller. I think 0.7 mil is the smallest wire we have.
Yeah, very small.
And
very, very easy to break.
yes, it's the most annoying thing to work with. You have to use a specific, we have so many needles that we've broken, you have to use a specific one for it. And if you overpower some of these needles, they break. And these needles are not cheap. They're like, I don't know, upwards $200, $400 each.
Yeah, and the wire bonders, I mean, they're extremely expensive on their own. And they can be up to $100,000 if you want like a CNC one or something.
Oh, yeah.
And we have essentially one good one in our lab. We have one bad one that died during the flood, which we will talk about at the end.
Yes.
But we have a number of projects which use these wire bonders, and they are essential to building the circuitry and electronics. And if you mess something up and you break a needle, you have thrown off everyone else's projects, probably for that week. So it's pretty high pressure to be very, very precise while you're using the machine.
Gotcha. What are the benefits of using wire bonding as opposed to something else?
What else?
Oh, I don't know.
Like your hands?
I think she means solder.
Yeah.
Oh,
Yeah.
yeah.
It does help with heat reduction. You don't have to worry about too much heat being transferred inside of the package or whatever your amplifier is connected to.
Yeah, so you don't have to press a soldering iron against your
okay.
electronics.
And you could have something that's really sensitive to heat, like the mimic chip for this amplifier, which you have the heat on too high, or if it's on there too long, the chip starts to kind of bubbles up, and the gold surface that you would bond to just kind of crumples and becomes gray, and then the whole chip just doesn't work. And one of these chips, they are also not cheap. Just to get 50 of them, I think it cost us about maybe $1,000 or $2,000 per packet. So just to get 50, or I might have that number wrong. I just know that just to order one pack was a lot, and we're not going to order any more for a while.
There's also, I mean, the heat is a big issue, especially for the stuff that you're doing. But I feel like the precision of it is one of the big selling points, right?
Oh, yeah.
The way it works is it's mechanic. I'm using my hands again on a podcast, but you pull levers almost like you're controlling a big, those diggers, the ones at construction sites. It's not the same, but you use a set of knobs and levers to very, very precisely place where you're going to be placing this wire down. And when you put it down, it has an incredibly small footprint too. So when you solder, you have a blob of lead solder that you heat up, and you shove your wire in, and it essentially electrically connects your wire to the actual board itself. But it leaves the blob of solder on there. And unless you are very, very precise in cutting off anything you don't need, there's a footprint from that solder blob. And on wire bond, you do not leave that same footprint. So you can get very, very closely lined up wires, all bonded to a surface in a row without any footprint. All of them are electrically isolated from one another. So you can miniaturize very complex circuits into a very small size, because you have this precision and cleanliness to it. And the lack of heat, which on a small electronics board is very neat.
Actually, wire bonding uses an ultrasonic tool to kind of just vibrate and kind of cut the wire when you're bonding it down. So you can control the force of how it's pressed onto that pad. You can change the heat and the ultrasonic power that just kind of cuts it and makes sure that it bonds onto the pad too. So I can't think of it right now.
But it's a pain in the butt at the end of the day. It is a pain in the butt to do, and you need someone who knows what they're doing to train you how to do it. And Justin is one of the few people in the lab we trust with the the NASA level machinery to actually do it. Justin and Hamdi are really the only two.
And when we had the old one before it got lost in the flood, we could spend upwards of 5 minutes to 4 hours trying to get one bond down.
Yeah, and then so the old wire bonder started breaking, and we realized it was the ultrasonic cutter. I don't know if that's what you call it, but the ultrasonic tool part of it. And Hamdi, we keep mentioning him, but for people who don't know, Hamdi is our engineering wizard in our lab. He's from Tunisia.
Yeah, he is a wizard.
He's
literally a wizard. He cold called a very famous professor at Caltech to ask him a question about low noise amplifiers when he was 18 or something. This professor, Sandy Sandy Weinrep at Caltech, just essentially brought Hamdi to the United States to work for him. And then my advisor, Chris Crappie, met Hamdi, saw how much potential he had, and was like, hey, if you come to ASU, we'll give you a bachelor's for free. So we got Hamdi, and he is easily one of the best electrical engineers I've ever met in my life. He is world-class, world-renowned, and is just incredible at designing these LNAs. He's the brain behind the designs for these things.
He also, this is a story Hamdi has told me, that he also had taken, a little background about Sandy Weinrep is that he's one of the foremost LNA designer and builder people out there. And that Hamdi, as he was under Sandy's wing, he took Sandy's design and improved it a lot, and which is where Hamdi gets his prowess from too.
Yeah,
he's the genius that he is, that he'll never admit.
I guess to maybe taking a step back, about the Simons Observatory project itself. and like why we keep talking about LNAs, right? Like we keep mentioning low noise amplifiers, and I feel like when I was first outside of the community, when I first got here, you know, we heard people talk about LNAs so much, and we saw people working on them that much, and I just kind of assumed it was just part of like any, you know, it was just the same thing as a capacitor or a resistor. I didn't really get the importance of an LNA and why Hamby was so renowned for it. But like they are such an essential part of most space missions, because you know when you think about looking out into space, right? What we are looking for is we are looking for very faint signals from either stars or galaxies or any other structures that release photons. You know, that's the communication of space. We're trying to listen to space in the electromagnetic spectrum, looking for photons, and these photons that come in are extremely weak because, you know, they're from hundreds, thousands, millions of light years away, right? It's a long distance for a little photon to travel all the way to Earth, go through our atmosphere or whatever else it has to go through, dust and stuff, and us to pick it up. So when we do pick up these extremely faint photons, we need to differentiate them from noise, you know, just general gobbledygook that we are getting. And that's where the low noise amplifier comes in. And it is a low noise amplifier because what it does is it takes that photon, that signal, or that, you know, that waveform that we are getting, we are listening from the stars, and it pumps it up to a point where it is something that is readable with human electronics. But the issue is that when you pump something up, there's all that gobbledygook in there too that also gets pumped up. And the point of the low noise amplifier is it essentially pumps up the signal that we want without creating too much noise, so that we lose the signal in all the other stuff that is involved in an electronic signal. And it is so important to the field of astronomy in general because everything that we use has to be amplified because everything is so faint in space. So in the case of Simons, and now I'm remembering now, Simons is, I think it studies the CMB mostly,
Yeah.
which is the cosmic microwave background, which is the kind of, it's the echo of the Big Bang, I think. Is the way to call it. You know, it's in a period called the last scattering. You know, the last time like the universe was small enough that electrons and photons were all in one area. There was one last period where the electrons all bounced off into space and they separated from the photons. And there is this very, very beautiful and unique pattern that a lot of people have seen before called the cosmic microwave background. And Simons studies this, and I mean this used to be, when you talked about cosmology, almost all of it was the CMB, because up until 20 years ago that was really the most important thing we could study, and we have studied the heck out of it since then, so it's a little on the wayside now, but people, I mean, still are very interested in it for obvious reasons. But Simons is working with ASU on this project to create these harnesses, and Justin and Handy's LNAs are, the low noise amplifiers, which are used for this harness. And I call it a harness because that's just what we call it. But it's essentially these massive cubes. And inside them, we have a huge layer of detectors that we call transition edge sensors. And I won't get into the physics of how TES works because I don't really think no one wants to hear that. But these are superconducting electronics, which means that we have to essentially get these down, as I said before, to almost absolute zero for them to function correctly. And the light comes in and it hits these TES sensors, or these edge sensors, and we have, massive arrays of them. And each edge sensor has its own line, which when light hits it, gives out a signal, and this line goes down to the readout system. And we've said the word readout a lot. And when we say, when we talk about readout in astronomy, readout is essentially the process of turning something from the physical world into the digital world, is the way I like to see it. You have these things that are happening in real space. You have these fluctuations in the electromagnetic field coming from a star, these photons. They hit some detector object, and this detector object reacts to these fields. And we take that reaction and convert it into data, which we put on a computer, and that's how we get these pretty pictures of space. So each of these lines comes down from this superconducting detector, which has a very small signal in it, and it goes through Justin and Hamdy's amplifiers, which amplify them to a point which can be read by a computer. And Simons is using a ton of these to do this large-scale mapping. And that's why Justin and Hamby's LNAs are so essential to the project. They have to be very good.
The project's using two specific design ideas come up with. I just did the board's LNA, which is the one that I built like 50 of them for, I think, a span of 3 harnesses that they've done so far. And then there's the 4 Kelvin LNA, which Hamdy is currently testing. I would say as we speak, he is very particular. He will not share anything with anyone until it's like he gives his seal of approval. Like, this is the best thing that you're gonna get, and you gotta buy it now.
Mm-hmm.
And no one will see it until like piece of art, like it's another testament to Hamdy's prowess. He makes it so good that people just keep buying it.
They have 2 stages of amplifiers because, you know, we have, it's weird to think about, but these photons are cold when they get a lot of orders, right? We are in these cold optics regimes, and we have to drag this information into a much warmer environment, right? So we're going from nearly absolute 0 to the temperature of your house. And through this process, the information inside these lines is getting all garbled up, because as it gets warmer, you know, the idea of thermal energy itself and heat is this extra movement in energy. And you are just noisifying, that's not the word, but you're adding in noise the warmer these things get. So it's a very, very methodical process of getting the signal in and having stages. The actual blocks themselves have multiple stages which are thermally separated. You know, the top is at 4 Kelvin, the middle's at 40 Kelvin, and you know, you go to 300 Kelvin from there. So there are these stages where we have to go from 4K and then slowly and you know, very precisely amplify the signal, move to 40K, amplify the signal, move it to room temperature and stuff like that. So it's a heck of a process. And this is used on a lot of other projects as well that we can talk about.
Gotcha. Yeah, I think Gusto has a similar process, doesn't it?
Gusto, I'm not 100% sure. It's not the same project, same process. It is similar to a balloon project that has flown twice, called STO and STO2. I've been there for the very, very first meeting. That's just mostly of what I've worked on. And I know that they have 5 amplifier blocks that have 8 channels each that are just reading out, looking into the CMB and reading exactly what John has mentioned before.
Yeah, I think also Gusto is, it's doing stuff. I do not work on Gusto at all, so I can't talk about it much at all. But I do think it studies like interstellar medium as well.
Yes.
And like that life cycle of the star picture, and how it's studying a lot how planets and stars form in these like stellar nursery areas of these molecular clouds of H2 gas, which is molecular hydrogen.
Exactly, no. Essentially studying like basically the birth of a solar system, essentially.
Yeah, the birth of stars. Yeah, and I feel like that's, you know, we really haven't talked at all. You know, we are technically a terahertz lab, right? And that's a deep rabbit hole to get into to really go over all of that. But terahertz is a frequency of the electromagnetic spectrum. It's a regime. So for anyone who is unaware, right, like all of the electromagnetic spectrum you know of, radio waves, microwaves, infrared, visible light, gamma, X-rays, all of that is the same thing. It's just photons, right? It's photons vibrating at higher frequencies and higher energies and lower frequencies. So just below visible light, we have infrared. And when I say below, I mean below in energy. We have infrared. And below infrared is microwave. And right in between microwave and infrared is this area called terahertz. And the issue with terahertz is that when you are in the higher energy regimes like infrared and visible light, you can use optics to essentially lasso and control your light. So, you know, when we want to look at visible light in space, we have that classic picture of the telescope with the optical, you know, the lens, the light comes through and focuses down. And when we are in the very low energy, which is long wavelength regimes like radio waves, we have lumped circuitry, so your standard circuit board. And that's because the wavelengths are so long that they don't change their energies at all on the scale of something as small as a resistor. But then when you get into the area or the regime where the wavelength of your light is at the same scale as the electronics you're using, you get very bizarre effects. And that is the terahertz regime. And it just so happens that also in the terahertz regime are very, very important stellar markers, such as water vapor and the CO line, which is carbon oxygen. So when stars are birthing in these stellar nurseries, these areas that Justin and Gusto are looking at, they give off very, very bright signals in the terahertz. And that's why we have to study this extremely difficult portion of engineering, because to be able to see these signatures, you need to overcome these massive hurdles of dealing with the freaky, bizarre, and almost unlike predictable physics of this regime.
Mention it. Gusto is a NASA-funded project. So all our work that we have been doing for this project has been in a clean room that has been NASA approved. Just to kind of oversimplify anything that John has said about Gusto, the Gusto project is to provide a complete spectroscopic study of all phases of stellar life, from the formation of molecular clouds through starbirth and evolution and the formation of interstellar gas clouds, and the reinitiation of the cycle. So as John said, like just the terahertz lines, carbon, nitrogen, oxygen, that electromagnetic spectrum. And it's set to fly, because I know dates are important, next December in McMurdo, Antarctica. Exactly what you want to know, unless you want to know like the process that I've been going through for Gusto and doing the instruments for it, or if you want to know more like.
We could also pivot a little into BLAST here, because this is pretty close to BLAST in the other projects that we all work on. I mean, neither Justin and I are essential parts of BLAST. And BLAST, okay, well, let's first say BLAST is similar to Gusto, because BLAST is also a balloon mission, right? And these balloon missions are done by launching essentially a massive weather balloon into the atmosphere at the South Pole. And we do it at the South Pole because of something called the polar vortex, which is this pattern of air circulation where if you launch a balloon into it, it can stay up in the air for an incredibly long amount of time, on the scale of a month if it's done very well. And attached to these balloons, hanging underneath them, are these gondolas. And on these gondolas, we put our telescopes. And telescopes in this case aren't these like lens things. They're actually these very, very complex detectors, these superconducting ones. And because they're superconducting, we actually have to attach a cryostat on that balloon as well. So this balloon flies up in the air carrying a telescope and essentially a super refrigerator. And we fly these around and we get tons of data. And this is essentially a way of doing a space mission for a fraction of the price. So space mission, if you want to actually go into space and have a satellite in space looking out, costs you on the order of $100 million, let's say, or more, $500 million if it's Class A. A balloon mission costs more like $10 million, and you can get very good data out of it for a tenth of the price.
We'll say like 10 to 40 million.
Yeah, 10 to 40 million. So as Justin said, they have done STO and STO2 as well, which they have flown. But very recently, the most recent balloon flight that was done was something called BLAST, the Next Generation, TNG. And this was based off of the original mission, BLAST, which was also a South Pole balloon mission. And there's actually a documentary about this.
Oh, no
called
way.
BLAST,
That's cool.
Yeah. The PI, Mark Devlin, who was actually at Penn when I was there, he was on the Colbert Report for this documentary, which was really cool. So, if you ever meet him, you can be like, hey, I saw you on the Colbert Report.
Mm-hmm.
So it was a somewhat famous mission that was done, and it was mapping the dust fields around distant galaxies. So galaxies themselves produce electromagnetic fields, which you can actually track by looking at dust particles. And dust particles in space aren't tiny little dots. They're actually like, you can think of them as like little grains of rice maybe. And they will actually orient depending on the magnetic field around them because they have a slight amount of electrical charge to them. So when they orient, when light passes through them, so you have, let's say, a star inside a galaxy, and around that galaxy is a bunch of dust, and that star is emanating light. And the light that is coming towards Earth passes through that dust. And depending on the direction that the dust is in because of the magnetic field, you will actually see different polarizations of the light. So by looking at how light is polarized from these stars, we can see which direction the dust is in, and therefore make an inference as to the magnetic fields around these stars, and these galaxies, I should say. And these magnetic fields are essential to understanding so many parts of the birth of stellar structures and stuff like that. So that was the original intent of BLAST. And they recently just relaunched it. When was the last time?
Last December, I believe.
Yeah, last December they launched it again, and this time they used a new detector technology. Before, they used the TESs, the ones that they use for Simons, the transition set edge sensors. And this time around, they used what were called MKIDs, which are microwave kinetic inductance detectors. I could, we've given this lecture 1,000 times. I won't do it here, but they are very, very cool technology, very good at detecting light. So they recently flew that one as well, and it failed.
Unfortunately, yeah.
Unfortunately, there was an issue where a collar fell off of the balloon, and they launched it, and it looked like a successful launch. They have video of everyone celebrating, and if you look at the video, you just see this like white thing fall off the top of the balloon, and it just bounces into this like $20 million mission gondola, and just like broke through like one of like the platings and stuff like that. Yeah. And it just messed up so much stuff that the balloon eventually just started to fall elevation super fast, and within a couple days it was on the ground. And not only did it land on the ground, there was, because of the way it landed, there was a pressure buildup, and then it exploded. Yeah. So this mission was supposed to fly for a month, ended up flying for like a day and a half, fell out of the sky, and exploded in the middle of the South Pole.
Yeah. Now, to be fair, I think they did get like several.
They did get some data.
Yeah, several hours of data, which is great.
And they're planning to do it again, though, aren't they?
Yes. Well, no, I don't know if Mark Devlin can handle that again. Mm-hmm. He has been through a lot of hurdles. I mean, space missions suck. It's like humans are not meant to be up there. Humans are not meant to be in the atmosphere. We are doing absurd things that take so many things going right to work. Mm-hmm. But when they do, it's magical, but it's so stressful. And Mark has been doing this for a very long time. And I think that he is starting to want to move on to the next thing now that they've been doing BLAST for almost a decade. But as a science mission, it was a failure. But as an engineering mission, this is the first time that we've ever flown these MKIDs and gotten pictures of them. It was actually quite a success. Oh, yeah. So in a lot of ways for our lab, we weren't too disappointed with the results, but the people who were waiting for the data about the, magnetic fields around the galaxies, they were a little disappointed. Yeah. So that, BLAST was BLAST. But we do base a lot of our missions off of that now. Mm-hmm.
So I guess to kind of back up a little bit, like you mentioned that, doing things in space is just incredibly hard. So, some people might think, well, why do you actually have to use a high altitude balloon mission in order to study that kind of thing? And there was a graphic that I saw, and it was comparing, just the difference of what you could see with a telescope on the ground,
windowing,
versus a plane like the Sophia telescope versus high altitude balloon, and then versus a satellite. And just because of the ozone, it's looking at things from the ground is so different.
Right, especially in terahertz, right? Mm-hmm. And this is with terahertz astronomy, this is the single biggest issue, is that water, there's a very, very powerful rotational line that comes off of water. When I say that, I mean the way the water molecule rotates gives off a spectral signature. It wobbles the electromagnetic field around it. And it does this in the terahertz regime, around like 556 gigahertz or 1.2 terahertz, right? And if you look through a terahertz camera, right, and you put your hand up, you will not be able to see it in front of your face. You cannot see your hand in front of your face in the terahertz on the ground because there's so much water vapor in our atmosphere. So if you want to look at anything in the terahertz, you have to get above the water in the atmosphere. And to do that, you got to get up like 100,000 feet, you know, and that's just the way science works sometimes. Because if you want the data, you got to put in the work and take the risk. And it sucks.
Is this your transition into Tim, or is it Astros?
Oh, I don't know. I mean, I know much more about Tim than Astros, but this would be the same. I mean, Tim, so I'm working on a new mission now. I feel like I've been talking for a while, so I want to stop soon. I don't want to take too much. I don't want to.
No. I told her ahead of time, like, just expect this, because I'm only as good at everything else as I can possibly be. Because mostly what I do is just build and test.
Yeah. Well, yeah. I've been,
because I came late on a lot of them.
So, anyways, Tim is the newest mission. No, I shouldn't say the newest. We've gotten more, but it's my mission that I've been working on recently, and it stands for the Terahertz Intensity Mapper, and the name is TIM. It used to be called Starfire, which is a super cool name.
It was great.
That's a cool name.
Yeah, apparently there's a DC superhero named Starfire. Yes. And when you Google images of Starfires, people were like, oh, it's a scantily clad teenager. We can't use it.
Okay, scantily clad.
Oh my God. Yeah.
That ruined it? You've got to be kidding me.
Sarah, I'm telling you, you said this is NASA bureaucracy. You know, like,
but
I love them for what they've done. I know. I love Starfire.
Okay, hold on. I think that would have been more of a legal battle than it is like a bureau.
No, I don't think it was. You know, I was there for the first. I was there when we made the name Tim. I voted on this.
Well, yeah, see, that's the story you should be telling, like how it became Tim.
Yeah.
I think you
okay. So yeah, we decided it couldn't be Starfire. We were at the first meeting. We had just spent like 9 or 10 hours going over every single portion of this mission, who was going to be taking over what, with all of these university heads from all over the world. And we go out for drinks later. And we were sitting there drinking beers, and we were like, we need to pick a name. We haven't done one yet. So we like tried to come up with some names. And I had the whole day been writing out like dumb names that I could think of acronyms that work. I had hilarious, you know, I thought they were funny because I have an awful sense of humor. I had ones that were called like Big Dog and like just stupid things like that. And like, they didn't get it. You know, I was just I was just a young grad student, and everyone hated me because that's what you do with grad students. So no one wanted to hear it. So they give out the list of names, and they're all awful. And they're like halfway through, I just saw Tim, and I was like, we had to choose 3. And I was like, well, Tim, no one's ever going to pick that name. So I checked it off, and everyone else had the same idea. So the PI of the mission was counting it up, and he was like, well, the official name of this NASA mission is Tim. And that was it. And we have to live with it now. So it works because we're mapping the terahertz intensity. We're trying to, so we're doing, it's the same thing as BLAST, essentially. We're using almost all of the same technology as BLAST, except we're using a spectrometer, a grading spectrometer for the light. So when the light comes in, instead of us just, measuring how much light is hitting, we're actually going to send it through a spectrometer and spread out the light through its spectrum, which means we'll essentially know how much of different frequencies of light are coming in, which allows us to do a spectral map. And from this, we can get some like really cool 3D, like volumetric mapping of galaxies and stuff like that. And it should be pretty cool. But it's essentially the same thing as BLAST, and we're going to be launching it up in the same type of gondola as BLAST, and hoping that it doesn't break this time.
Hopefully.
Yeah, and the other difference, right, and this is the part of the project that I'm working on, is the readout, which I said is the kind of the change from the physical world to the digital world. And this is easily the like grimiest part of like space missions that I've worked on. I never wanted to do readout, but you always end up working on the projects that you never want to work on. But this is done through what are called FPGAs, or field programmable gate arrays. And it's like, if you think of like a CPU in your computer, your CPU can either add, subtract, or multiply, and it just loops through these functions over and over to do your systems. An FPGA is almost a more fundamental version of that, where it's just think of like a massive grid of logic, right? It's just a bunch of NAND gates. and you orient these things so that you can do incredibly high speed, high bandwidth processing of information. So where a CPU, where if you wanted to do an action 1,000 times on a CPU, it would just set up a loop where it would do it 1,000 times. On an FPGA, you set up the logic so that you put the step 1,000 times in a row, and it just shoots the information through and goes in a row and does it 1,000 times through the board. And these things are incredibly difficult to program. They are super, super basic, fundamental information theory and data theory. And it is brutal to work on. And we have used the same FPGA for 10 years called the Roach. And it's as disgusting as it sounds. And we have some people in our lab, specifically like Adrian Sinclair and the undergrad Ryan Stevenson, who are very good at this. And Adrian in particular is world class at this stuff. He'd say he wasn't, but we recently, this new FPGA has come out called the RF SOC by Xilinx. And it is just like, it is, the next coming of the Messiah when it comes to this stuff. It is able to process, like 8 times the information speed. It can do it all with, an eighth of the volume, an eighth of the power consumption, but it is completely untested technology. So our lab has, and I've been working with this, has been bashing our head into this incredibly complex logic board, trying to form it into something that can read out this balloon mission. And on this balloon mission, we're looking at 1,000 to 2,000 detectors, which, we have to be able to read out each of them, like a few hundred times per second, and get the information out of them in a way that can be then transferred to a computer and read. And the difficulty of this is that, like, there are all these things that can be done in hardware to make life easier, but they don't. If there's something that goes wrong in the actual detector design or something like that, it is very easy to say, okay, we'll just put this problem onto the readout team. It's almost like the post-production team on a film. Like, oh, that shot looked like crap. We'll leave that to the post-production editors. That's what readout has to do. So it has been this brutal climb of learning this technology and trying to get this new technology to work for this. And recently I've kind of moved more to the software side of things, where I'm working on the actual communications with the balloon, doing flight software. So with these balloons and missions, I've now worked on the hardware and SolidWorks and design of it, to the firmware side of it, to the software side of it. And it's been a huge, long road. And hopefully Tim will be flying in 2024 or 2025, but who knows with COVID.
Mm-hmm.
Yeah.
And most it probably just pushes it back a year.
Yeah, I hope. I won't be around for the flight of Tim. I'm only going to be here for a couple more years. But yeah, I needed to get that off my chest. Yeah, my God, no one knows about readout. No one has ever heard of this field before, except for very few people. No one knows what an FPGA is. But everything you do, it has at some point relied on some lunatics in a basement of some building programming an FPGA.
Yeah. I mean, you guys are insane for even trying to mess with that. Watching you guys every day deal with the RSOC, just like kind of losing your minds. It's like entertaining, but at the same time, it's like, I am so sorry for you guys.
Yeah, it is like staring into the void, and the void is looking back at us. Yeah.
So then what does the communication side look like? Like, is it RS20, RS422, or something completely not standard?
Yeah. So I'm actually not sure exactly how the flight software works for BLAST. So in general, the goal, right, is that you are able to essentially send a command to the balloon and your FPGA does some function, right? Because when we're looking at stars in space, we need to recalibrate things. Like the way these detectors work, like it is difficult to impress the complexity of these things. The way they work is we have to send a probe tone into each of the detectors, right, at some central frequency. And when light hits the detector, the output frequency changes and the output phase of that signal changes. And to do this, we have to do this for each of the detectors all at the same time in a process called multiplexing, frequency multiplexing. So we have to send out thousands of very specific tones, which hit these detectors, and then come back, and we have to read in the tones, see how much they have changed, then calculate how much incident power that relates to on our receiver. So the more power that's hitting our detector, the more photons that hit the detector, that means more of a frequency shift.
Okay.
So you often need to recalibrate because your frequencies will shift further and further. So you have to change that central tone. So there's all of this kind of like real-time work that needs to be done on these balloons that needs to be controlled from the ground, because obviously we're not on the balloon with it. So the main focus of the flight software is being able to communicate with the balloon and have the system change on command. So what we're looking into right now is this open source, this kind of open source platform called Redis, which is a very simple networking protocol. And I just got in contact with the Redis people last week and told them about our mission, and they sent me the Redis for Dummies book for free.
Hey.
So I am now reading Redis for Dummies to try to understand the flight software here.
Nice.
But all we want to be able to do is send a packet of numbers or information or something through Redis that will hit the on-system chip on our FPGA. That's the reason we call it the RF SoC. It's a radio frequency system on a chip. And that system on a chip will be able to read in that signal that we send, run some sort of Python script built into that, and that Python script will then communicate to the FPGA. So right now we are just getting basic Redis communications to work. We're sending communications between computers. You send a funny word, like, I don't know, something like keyboard and it responds cat or some other dead meme or something like that. So that's about the point that I'm at right now, but slowly we'll be transferring that into something that you send in a packet, let's say 22. And, on the giant list of commands, 22 is known as the recalibrate command or something like that. And we write a Python script that we load onto the board that goes on the balloon and runs that. But there are so many, there's so many ifs and buts at that point, right? Like, can this board, this RF SoC board that is super new technology, can it even fly on a balloon at 100,000 feet? Can either of you answer that? Because I sure can't.
That's what you're supposed to be using
the vacuum chamber for. Yeah. So there's so many things that need to get done before we can successfully have a readout ready for this mission, and it's a long road ahead of us. Yeah.
Gotcha.
So that's why I love the lab, and that's why I feel all of us do, is because we have these daunting missions ahead of us where there are so many unknowns and you are staring into the void. And the beauty of the lab is that when you get overwhelmed, you just turn your chair to the left and you just hop onto the project next to you for a little while and do that instead.
Well, that concludes part 1 of this episode. If you want to know more about testing LNAs, the lessons Justin and John have learned from their experience, and the story of the Great Basement Flood, then check out part 2 for more basement shenanigans. Don't forget to follow this podcast and like it on Facebook for further updates, and I'll catch you all in the next episode. Here's looking forward to future adventures and the lessons learned from them. Cheers, Sarah.